Okay, so I am so pleased to announce our speaker, Mr. Frank Hughes, who's retired from NASA as Chief of Spaceflight Training, highlighting training and accomplishments of astronauts during the Apollo, Shuttle, and Space Station programs. His extensive NASA career began in 1966 while he was involved with the Apollo simulators as an instructor, with expertise in the Apollo guidance computers and cislunar navigation. He has been involved with every manned spaceflight since that time. When leaving NASA, Mr. Hughes headed an organization responsible for all shuttle and space station training for astronauts and flight controllers. Since leaving NASA, Hughes joined Titronics software, okay, where his responsibilities included the development of new technologies for operations, training, and education, including VR, AR, and mixed reality training. Take it away, Frank.
Okay, Alex, thank you very much. And thanks to all of you. I kind of just horned in here and made some space, but I'm glad that we have a chance to talk tonight. In talking about navigation, it's in your neighborhood. It's actually the things that you do. And yet the things that you do routinely were impossible only 400 years ago, or 500 years ago, I guess now, as we're getting into that level. Navigation was a big thing for me when I was growing up. I grew up in Montana, so the skies were great. Problem is that you damn near froze to death because you're out there trying to see something, but it's 40 below zero or something. Anyway, as we look back through history, a lot of stuff went on. Remember when we were sailing on the Earth, we didn't go any further than you could be out when you could see the Earth. You could see the horizon, or you could see the shore all the time. They did a pretty good job with that. They moved all the way around the edges of Europe and around Africa. So all those kinds of things worked very well until we got sextant, and then sextant gave us latitude, since we understood how that worked. And finally, with good clocks, we were able to find out where we were longitude-wise, and that took us people off to the New World and all those things. It worked out really well, down to the point where today, GPS is just, it's everything. It's everything we go. In fact, I've met several, it's kind of scary that young children don't know how to get to school if they don't have the phone with the GPS. They don't have any regular how to get home kind of information. It's just not being built into people. That's a different subject and a whole other conversation. But the fact is that here we are when I guess I'm gonna share this screen now. Let me do that. Okay. Jack, you need to give me the screen, it looks like.
Oh, Eric, I think you're in control right now, aren't you?
Yeah, you should be able to share now.
Okay, thank you. Good. Yes, let's do it. Okay, this is what I'd want to talk about if we go through this stuff. I got to clear up my screen here. Okay. Because what I want to talk about is celestial navigation then versus cislunar navigation in the future. Now that's only means navigation in the area of the Earth-Moon system. That's the name cislunar. But of course, we're going to go further, and we'll talk a little bit about that. If you think about it, in space, navigation only is one part of the three-legged stool, part of guidance, navigation, and flight control. Navigation allows to know where you are. Guidance, obviously, has the idea to compute how to get where you want to go. And control allows you to use the engines and other effectors like wings to get you there. So that was when I drifted into NASA in 1966. It was a new world. It was a very new world. For example, you guys, some of you are old enough to remember Mercury, and in Mercury, it had no navigation. It actually had no ability to change the orbit that was in. We sent 6 people up, 2 suborbital, 4 orbital, and when we did it, they would be launched into an orbit. They stayed in that orbit. They had attitude control. That is, they could look around, but they couldn't do anything about it. And then when they turned around, the only thing they could do is point backwards, fire the retro rockets. There were 3 of them, and that slowed them down enough to drop back in the atmosphere and come home. So all of that stuff, they didn't have the ability to compute it, anything. And that's why some of the early pilots that didn't want to be astronauts called that being a spam in the can. That is, that they just went and lived there and came back. I could tell you whole stories about that. We could go down what it was like to do that, living and working and so on in there. But let's just say that it got done. There was not a computer on board. There was not anything except an environmental control system, some ray gyros to hold attitude where you pointed at it, and so on. And so we come to Mercury Mark II, which we actually called Gemini. I mean, it started out being called Mercury Mark II. But Gemini, now they got 2 people, and they were launched just like the first one by a launch, which is a military rocket, which subjected the people to some really heavy Gs. They routinely got 6, 7, 8 Gs on the way uphill. And so that's why we needed to have test pilots and people who were ready to put up that kind of grief. I get through this stuff. I would go a little bit faster here. The big thing about the navigation is that we had none. And the reason we had none is there was no computer. That actually, the vehicle that you flew, it was all manually controlled, and that was it. Now, when we put it together, it was a big, big step on the way. We had 2 people side by side, and I mean side by side. They were right shoulder to shoulder. And they had now a 4K computer. That is 4,000 locations of memory. That was it. But it was what they needed to compute rendezvous targets. They would be still launched into orbit by the rocket that we did. We used a Titan rocket. And then once they were there, though, they could affect the orbit. They could change the orbit, lower, higher, getting to the target vehicle that you're after. And we needed that because rendezvous was important for the Apollo flights that were about to come. It was a very simple machine. It was used for computing rendezvous solutions. And it was one of those things where you talk to it by putting in a 3-digit code, and after it had word and crunched and did whatever, it'd give you a 5-digit response, mostly in the terms of distance or length or whatever. Remember the pictures of this thing. The people were here in the Gemini, and this is where all the service module stuff was, propellant, electrical, things like that, fuel cells, things like that. This is a picture taken from Gemini 6, Gemini 7. This happened in 1965, late near Christmas. But if you're inside, this is what that Gemini looked like, okay? Because you had 2 people, each one, they could back each other. The commander over on left side and the pilot on the right side. But on the pilot, one of his jobs is to run the computer. So this is down here in the lower right side, circle it with the mouse, that's where it is. So you would key in the numbers, and then it would come up here and display things like that. And that worked very well. But imagine, it was a big step to put something like as big as a 4K computer. I mean, this was a gigantic step forward. Now, in order to go to the moon, we need to have a much bigger deal. Navigation to go to the moon meant the primary navigation was going to be from the ground, where they used radar tracking, things like that. But Apollo had a sophisticated onboard navigation scheme that get the astronauts home if all of the communication failed. And star sighting would be used to allow the crew to keep their inertial platform aligned. And for those of you not with me there, but an inertial platform is just a gyro-stabilized platform that once you tell it where it is, it holds that attitude, and then everything that you do is based referencing on it. The big thing here is to take this navigation to a whole new place because you didn't have a horizon. Everything we did on the Earth is you measured angles with your sextant from the star or the sun to the horizon. Well, now the horizon doesn't exist out there, or you're so far away, like you are on the way to the moon, that you're just surrounded by stars. Anyway, there was a couple of things you could do. Star sighting, instead of star A and then star B, that would give you all the information you need to get the platform aligned. Or you could do a star to a planet limb, or to a landmark on that planet, and you give you a decent position about where you are in deep space. And I'll talk about that in a minute. This is a big thing. You could also use it to track landmarks. That is, remember, we're going to go to the moon and we're going to try and land on spot. And that kind of thing took some very exciting navigation kind of things. The first primary was still with the government on the ground telling you where you were. But after that, they moved and navigated spot. So they got a good update from the ground about once a day. And going on here, these are some of the actual charts. We had to, let me get some of the things that you know. We used to teach this to the astronauts, and here's Dipper up here, and you'd follow the arc to the Arcturus and speed on to Spica and continued on to Regulus, you know. So all these things, we taught them, and they did a pretty good job. Here's the other side of that one. This is actually a copy of a chart that would have been on board with them. And you could see Castor and Pollux in here. You could do the same kind of thing for go through Procyon down to Sirius, things like that. And you know all that stuff going on. Here's the deal. When you go back for it, each spacecraft needed to update that orientation of the platform so it can determine where it was pointing and then where it was going to thrust in order to get to an objective. The sighting on at least two stars would allow the computer to realign that platform, and also it would give them an idea of how fast it's drifting, because they all did drift some. Generally, the platform alignment was only done once a day, and that was pretty good. It was easy. The thing is different. It's easy to maneuver the spacecraft, or in the case once the lunar module was flying on its own, either spacecraft, while it get to the point the Sextant telescope near a target star. Once the lunar module landed, though, alignment is a lot more difficult because now it was not floating in space. Let me go right here. In the case of the Apollo command module, it had a steerable sextant and telescope. The telescope was a 1-power finder thing, and then the sextant was a 60-power, really decent piece of optics. And it worked out really well for them. But the thing is you'd then point to the star that you're getting up to, and when you'd hit a mark, you'd hit a button, then the computer would copy the angles on the platform and transform all that stuff into where you are. It's a state vector, we call it. The computers kept track of where you are in this coordinate system that's Earth-centered. That is, we're flying through a system where when I took a state vector, it'd mean you would have 3 position, 3 velocity values, and the time that occurred. And for Apollo, those things were in feet. So it was millions of feet from the center of the Earth and so on. And the machines did a good job of keeping track. But then you use the gravity equations to propagate that under the gravity that you know what's going on, so that you can figure where you're going to be an hour from now or a day from now, whatever. Now, I want to go back to it. This is the Apollo command module, okay? And by the way, the off color here is because this is not computerized. This was copies of some of the actual documents we used, and over age, the white pages have changed a little bit. But you get the idea that in the spacecraft, now the people are up here, this is talking about landmark tracking, but also you just do 2 sightings and they'd give you star sightings and then get the platform. Or you give these other things to do landmark tracking, and you could out of that, you could find out where the heck you were too, relative to the ground. Now that is a big problem because you had to know where the thing was on the ground. And when we started out, the error is there in the order of miles. If you had something good within 2 or 3 miles, you were doing real well. Well, that's not good enough. This is a command module. And if you look at it, these are windows looking at it. And down in here, this is where the sextant and the telescope look out into the world. So you actually have to leave your chair and get down in what they call the lower equipment bay and look out at these optics and talk to the computer down there. Just another view of it. Here's where the people are. This is your docking equipment and all this stuff. And you'd go through all of these things. This is that area where the get around to it. Right here is I couldn't find any really good pictures to show the optics as it points outside. But you get the idea. It didn't raise thing. The optics was quite good. This whole thing was programmed by MIT Instrumentation Laboratory, and all the equipment, believe it or not, was built by, or most of it, by AC Delco. So General Motors at the time had a big chunk of the equipment for Apollo. Now, in order to get somebody trained to go, we needed to have simulators, and that was the job I had at the time. I was an instructor on the shuttle mission simulator. Simulator was able to teach the crew members how to do star sightings using the maps and the telescope. It's a finer scope. One big larger problem when you got away from the Earth, we launched the people around Mercury and Gemini, but we were so low that it pretty much was like flying a big airplane, and that is a very high airplane. When you leave the Earth on Apollo 8 for the very first time and get away, you realize there's a problem that we didn't think about. It was difficult to find the constellations because there were so many stars visible. It's not like anything, even on the best night you've ever seen, although if you've been out sometime in the country, you know how many stars are out there. Well, multiply that by 10. It was almost a gray star haze across the sky. So they had a real hard time finding out where they were. It's because it's like too much data. You're just overfilled with data, and there's so many stars in every direction. And that is every direction. You're looking up, down, left, right. There's stars everywhere because the Earth is a big circle, but it's over there about, look like 2 inches across. Yeah. Each window in the simulator, we had a set of visual systems that was put together by Ferrand Optical, who was in the Bronx when they were building all this stuff, and right down the road from you there. And of course, Singer Link was the one who was building this whole simulator. So each window that the astronauts would look out, there was a 30 diameter ball, a star ball, and it had 999 steel balls countersunk into it. If you illuminated the stars with a columnated light, they created a really, really great star field. And because you get what's called a specular reflection on each of the steel balls. So this is one of those things, years after it's been used, we've, up in Binghamton, I've been working with a group that they've got a TechWorks museum up there, and they've got some of these star balls, and we're actually trying to put it together so that you'll be able to go up and look out as though you're looking through the Lunar Module telescope or the Command Module telescope. You can see here's the Pleiades. You get down in here, some of the stars. We give you a test here. When we go through, there were 6 sizes. These are all steel balls, ball bearings, and the bigger diameter of the thing give you a bigger, brighter specular reflection. So there's actually 6 ones, some of them very tiny, down to about the 5th magnitude, and the biggest ones produced something in the -1, -2. Now on the Apollo lunar module, it was easy to do the same kind of thing. It could fly. We're not going to work on all the matrix math that had to go through this stuff. But the AOT was up in here, okay? It poked out the top of the lunar module. And if you remember, this is what a lunar module looked like. So it was right up here. You could just barely see it there. This is where the 2 guys would be looking this way. Now remember, there's a couple things going on. First of all, here's Pete Conrad and Al Bean, who was on Apollo 12. This is that telescope sticking down through the roof. Okay, so this is, when they're flying along, there's not a problem to line the platform and do a star sighting at all, because you could just look and maneuver the spacecraft. You grab the hand controller down here and twist around until you found the stars, and then there was a place where you marked the buttons. Here's another view of it. Here's that telescope. By the way, this is the hatch that you would go through to get into the lunar module, command module. It'd go up there. There was a tunnel between the two. But I'm going to go back here. Once you landed now, see, there's a real problem. Here's that same AOT, but now you can't maneuver. So what you have, this is the AOT, and you actually had positions. You would twist it around until you got the stars in that you want to use, but the field of view is quite large. It was almost 90 degrees. But so by looking at that, you knew one orientation about the spacecraft, but then you still had to do this other thing. By the way, this is if you look at it, here's the telescope sticking through the hull of the spacecraft, and over on the side of it, this box over here looked like this, and this button's where you'd actually push the mark button, and if you didn't like it, you reject that mark and do it again, and so on. But you'd mark an X and a Y coordinate, and that range. But here's the magic that they did: the reticle that you're looking through has these Archimedean spirals on here. So you twist it around and get the X angle, which was what's going on here, back and forth. And then as you twist it around, you get the Y by how far that star down here is along here, okay? So you'd do the shaft angle down here, and then you twist it further until you come around and get the Archimedean angle on it. And that will tell you how far it is on the other axis. And that whoever came up with that was a genius, and it worked really, really well. The stars were able to present themselves. They were very stable. The stars were stable in that case, but the lunar module couldn't be moved. So by doing this simple field of view, and then you would twist this thing around and find out, and then mark the angles. Now, let's go back a moment. Let's think about this. We're in orbit around here, not there, but there. Okay, and this was, by the way, around the Earth. This was a test lunar module. Some things you don't know about the lunar module, by the way. You see these things running down. Anybody can light up and tell me what those are for? This is the stairway you see all coming up and down over here. Okay.
Ground sensors, aren't they?
It tells you when you're getting close to the moon.
It's
Very
actually,
close.
yeah, that's right. That's right. Those are 5 feet long. Okay, and if one of them touches, all it did is turn on a light inside that said contact. And if that means if you're within 5 feet, that's good enough. Then you just reach over and shut off the engine, let it just fall down. Okay. So the first thing, when we got to the moon, Buzz Aldrin, first thing with the moon was not about Houston and about anything else. It was contact. Okay. And then they went through the things to shut the engine down and let it plop down to the moon. All of those things went on. Go back over here. Now, in the navigation in the Earth-Moon environment, though, it's complicated because you don't have an idea what's going on. Everything is moving. You're moving in your spacecraft. The moon is moving. The Earth is moving around the sun. All of this stuff. So there were no stable positions to take any of these measurements. So Draper Lab came up with the idea that you could take sightings of a star, and then the angle to a landmark or to the limb would take that. If that's a big thing, you do it. Now, and I know what you would do, that angle, you would create a solid cone by rotating that angle around that vector. Okay, think about that. I brought along, can you see me here on, bring up the picture. Can you make that happen? Let's see.
We can see you.
Yeah, okay. I want to make sure I'm making it big enough. So the center line of this funnel is like that cone, okay? So once I take a picture of that star, then I create a set of cone, one cone. And now I'm going to take a picture of the limb of the Earth. It's another one. I can't do it in these things, but if you could slide them together, okay, pointing in different directions, what would the only place there would be is a line on each side here, which would be, you have to be on one of those two lines because where the two cones come together, okay? And that, if you did that, you're in pretty good shape because you know one of them is better than the other one just by dead reckoning. You know that that other angle is, or that distance is too far from where you were yesterday. So then
You'll have to share. You'll have to share again. I turned off your sharing so we could see your demonstration.
Oh, okay. I'm sorry, let's do that. I thought I had shared it already. There you go.
did. I turned the sharing off so we could see a better view of it.
That's okay. All right.
Yep, we're back.
Okay. Anyway, bigger thing, so you can see the cones. And then if you get the idea, if you create two solid things, if you look the cone, the angle of the star, and then you take that angle, and if you do it, you rotate it and you create a cone, two cones. If you put one for the Earth and one for the limb of the Earth and one for the star, then you'd get the only place where those two cones look would be along two lines. And since you know where you were yesterday, then it tells you they're on some line like that, and then you just accept the answer. Right? If you have questions, we'll come back to that. Let's just say, anyway, that worked very, very well. You take that second sign, get a different cone, a different thing, and put it together. I've got some pictures here. So now we're back to sharing, right? You got the picture now of the two cones?
Yes, yes, yes.
Yeah, you don't want to see a picture of me. That's all right. Now here's a spacecraft out here in space. Okay, you're way away from this planet, whichever one it is, Earth and Moon in this case. We know that the stars are unmoving, so that we just assume that vector coming from that star. So if you take star one down here, measure this angle to, I'd say, the landmark, or it could be at the limb of the sextant would allow us to just take and extend it down just like you would on a Earth-based sextant. Okay, just come straight down to the Earth. So you get it in a good angle. And now if you twist that angle, that gives you, that's that cone. Then you take another star for star two, and we create a second one, okay? So you get the first cone, second cone. Now you can see that in the solid geometry, you're only going to get two lines where those two cones touch each other. And so you got to be along one of those two lines. And then, like I said, for dead reckoning, then you wind up, you choose this as the answer. That's the update. So when you say that, then the computer accepts that and updates its state vector so you know where you're at. Now, that went on for a long time. I mean, we did everything. We never have to use the spacecraft, never had a failure in the communications, the ground, radar, and everything else worked fine. Everybody got home. When we went and do Skylab, when we went to do shuttle, we're still back to where we were. We started out. We're close to the Earth. We're not 300 miles away. So it's another also interesting thing. On phase one spacecraft, it's really simple. If you break it, bring it home and we'll fix it. Okay. Type 2 is a different thing. It's like space station. You can't bring it home. I mean, it weighs more than 1 million pounds. It's got so many piece parts on it. You can't bring it home without destroying it. And so then you have to have a system to bring up spare parts and everything and fix it into place up there. That's a phase 2 kind of spacecraft. Phase 3, now we're talking about if you go to Mars, because you can't bring anything back. You can't bring enough spare parts along to fix it either. You have to figure out how to fix it in place when you're going out there. And I was staggered for that for how many years, but the fact is now, suddenly with solid state printing, you might have the ability to do everything we need to do. We just have to bring raw material, make new parts, put them together. As just the same, you may be able to make and print food for you, or and so on. And the trick is, if you're going to go on a long distance like that, then you have to be able to recycle the old parts back to the basic ingredients so you can render through them, remake them. Now, the future, let's go to this. You guys were saying you're just talking about, you're going to talk about neutron stars in a couple of months. Fact is that Earth is still just trying right now and trying to get back to the moon and then on to Mars. This is moon probably, in 25, maybe 26, 2025, 2026. But how about we go further? What if we want to go interstellar? What are you going to do? You see, all kinds of things. Long time before you get there, then the old methods don't work. Now, there may be GPS that we put in orbit around the moon or around Mars so that we have navigation aids and all like that. But that's to be done still, okay? Now, if you're going at some percentage of the speed of light, let's say you can get up to 2%, that means you'd get it to Alpha Centauri, 4.5 light years away. So hell, you're talking about 200 years to get there, things like that. If you go on 10%, still a long time. But how do we get there? How do you navigate out there? What is out there in terms of other things? We're working real hard on rocket propulsion to get us to Mars so you can do it in 3 weeks as opposed to 9 months. And the idea is the longer you stay out there in deep space, space will go get you. I mean, there's just enough things that'll hurt you really bad, and you don't want to be just poking along at a very slow speed. Anyway, as you get out there, what is your current position? How long are you going to get there? None of those old methods are there, because there's no planetary bodies up beyond the Oort cloud or somewhere out there. And so what do we do? Now, one that I've been working with some people and discussing, I didn't invent this, but the fact is that they were there, which are the Cepheid stars. Okay. Now, you guys might have even done some work on those. This young lady, well, young at the time, 1912, Henrietta noted that there was 25 stars. She was at Harvard. And these Cepheid stars, they're in the Magellanic Cloud, and they would brighten and dim periodically. She was able to measure the period of each of them because measuring the time and its up and downs came out in brightness. She was able to decide the brighter ones, the longer the period. So a Cepheid does this kind of thing. And this is in days, and this is apparent brightening. And these are marvelously interesting stars. Well, what the hell does that look like except a clock on a GPS satellite, right? In other words, we could use stars, create a system where we just have our now automated star trackers measure this one, because when you point at this one, we know where it is in a relative sense on the heavens. And we know it's this one because this unique periodicity of the thing. And then from that, we get a lot of information because a period leads to luminosity. You can reduce that to, of course, the astronomers, what they do is care about what kind of star it is and how big it is. We don't care about that navigationally. We just want it to know its name so we know its place on the heavens, and then that can move forward. The Cepheids, their usefulness has been very special. The period, the time they take to brighten, dim, and brighten again is regular, and that's really important. And then it's uniform. It's a uniform function of the brightness. So there's a relationship between the period and the brightness such that they really know it. And that's really good, like I say. They've done really a lot of things to determine it. In fact, the Cepheids are the first time that they could really say that the Andromeda is not just a satellite of Milky Way, like the Magellanic Clouds are. It's way the hell far out there. And suddenly they could see Hale was able to say that, this universe is really big. And of course, he didn't even get an idea how big it is at that moment, but you get the idea. They rewrote the book. Anyway, by the way, just this is extra credit. For those that you're wondering, I can say, well, what's happened to this star? Any of its stars, some of them big. The smallest ones are about 400 sun mass-wise. But helium they thought is a gas that's most active in this process. Helium, if you ionize it, you can still look through it. But if you double ionize, that means you ripped off both of its electrons, okay? Then it becomes opaque. And so the more helium heated up, the more ionized it becomes, then that makes the dimmest part of the cycle is when the ionized gas is really, really hot and really opaque. So it's heated by the star's radiation and so on, begins to expand. Well, as it expands, it cools off, becomes less ionized. It drops down to just single ionized things, gets more transparent, lets the heat out, and then the thing starts all over again. So it's expanding, contracting, kind of like this, and you get going. That's the process, but it doesn't matter. But all we care about is that we can see it and say, just like we say, you have to have 3 GPS satellites to get a really accurate position of where you are. And that would be the same with the Cepheid. Now I'm going to hold up there and let you guys ask questions and talk about it. We can double back on any part of this we're on. I just want to go through this quick, give you something to think about, and see where we're going to go on the next steps out.
Cool. We do have one question in chat for Mark Dillon. Mark Dillon, you want to go ahead and ask your question? He's still there?
Yes. Thank you, Mr. Hughes, for being with us tonight. My question had to do with the moon landings, and you talked about how it was very interesting about the Mercury astronauts being what we call spam in the can. They didn't have any control over anything. But then we get past Gemini and we get to Apollo. Now you got Armstrong and his successors landing on the moon. And my question is to what extent they were pilots or spam in the can, to what extent did their human decision-making affect the success of the missions that they had?
Well, that's a really good question. Let me say, let's go back to the spam. Chuck Yeager said that, okay, at the time. Chuck was asked to become an astronaut, and he said, hell no. He didn't want to go up, and said because the Mercury spacecraft was pretty much spam in the can. By the time that we got to the Apollo, the spacecraft was enormous. I mean, the fact is, I don't know if you know, but it was the memory system was 36K of memory. So, and yet at the time, that was really special. And the fact is, we could compute and land on the moon based on navigation on board. And it certainly could at least propagate those vectors and know what's going on. So by Gemini and Apollo, they were acting as pilots. They really were flying the vehicles. They were navigating all the time. They were certainly working in concert with the ground, but it was a big deal. Okay. And as time went on, it just got better. It's interesting when Chuck was saying that, by the way, the airplanes he was flying, which was A4s and 8s, they didn't have computers either. It was a point and shoot kind of airplane. Okay, it was like the World War II kind of thing, where you just got behind somebody and open up with guns and so on. Now, when the second group of astronauts came in, they'd been flying F4s in Vietnam. So that was a much better airplane and so on, but better than anything that Chuck had flew, although he ultimately flew F4s. But his thing is back on the X1, LX1, where he just broke the sound barrier and so on. And to do that, he had to go downhill. So it's like that kind of thing. They were really good pilots. What we trained them to do mostly is to get home. Okay, everything about it was what if. And so we went through all kinds of malfunctions and so on. Anybody that went to fly, first of all, they knew how to do every system on board. And then you did the malfunctions for every system. And then you did do 2 or 3 contingency things. Contingencies, fire, rapid delta pressure, get a hole in the cabin. It's not so much in those vehicles, but you could care about contamination in the atmosphere, like the chemicals that you absorb CO2. That kind of stuff would get loose, and so you couldn't breathe. So all of those things, that's a training. But they came in the door being really good pilots, and they went out the door to fly with being better pilots, okay? Because then you had to know it's not just like wings and it's responsiveness of the vehicle. Now you're going reaction jets that you fire, and you have to wait for the vehicle to turn. You don't just flip it over into a 180 anytime you want. You did it to control fuel, maximize. Like I say, we want to give a reward for everybody who brings the most fuel home, because that means they're home, and they did it in a prudent manner. Did I cover your question or is there more? Feel free.
Well, I have a follow-up on that. If the movie Apollo 13 was in any way accurate, they had a lot of input because they didn't have a lot. They couldn't use a computer. They had to have everything shut down basically, and they had a lot of trouble. So they had to do a lot of hands-on, didn't they?
They did. Scott, it's really true. You picked the one that's really tough. The fact is, as you know, if we had landed on the moon already and they were on the way home, we'd just see them die because there was nothing, the vehicle, the lunar module wasn't there to act as a lifeboat. Okay. So we just saw them. They'd actually would have flown back toward the moon, toward the Earth, and then they would miss the Earth because right then they didn't have the right orbit to get into landing. And so what they'd have done is they would have died on the way. When they passed the Earth, do you know what that treble clef is, on music, where it's a funny looking thing that it goes up and then straight down. They would have done that, like they'd flung over the Earth, throw it high up in the air, and then just come straight down and burned up. So it would have not have been a fun day. That still will happen. Someday we're going to lose people in orbit. We've left them launches, we've lost them under landings. We've not done anything where we had to leave somebody behind. But in the big words of the world, that's going to happen someday. We don't want to think about it. Believe me, I've lost 17 good friends. Apollo 1, Shuttle 25 and Shuttle 107. So all of those things are just tough business. But it's a tough business anyway. If you think any of these people that fly, the pilots especially, when they get to be astronauts, when they actually approach and land, get in and get themselves in NASA, actually half of the people that they were flying with are already dead. Okay. And it's the type of business it is. You go out and push the edge of an envelope on a new airplane. The whole idea being how far can you take it out there and keep flying and get to fight. Well, the fact is if anything bites you, then you're gone real fast. Okay. It's an interesting thing that on 107, the one that we lost in 2002, when it came apart, the vehicle was so good, it's coming down, and they had a big hole in the left wing and the root of the wing. So it got more and more drag. And the computer and the guys kept fighting it. It kept trying to do this, and the rudder and the fire jets, and it kept on going. And it was just fighting to just make it to ground anyway, all the way. The design was so good. And the only thing that they lost it is then the left wing broke. I mean, all the plasma got inside, melted the structure of the wing. And once it folded up, it still fought it. It did a flat spin all the way around until it came up on the third side, and then it just came apart. Aerodynamics is such that you just can't fly big airplanes high speed sideways.
I had a question also about Apollo 13. So
Sure.
of the multiple problems that they had to deal with, how many of those had already been enacted in simulator training, and how much had to be figured out exactly on the spot?
I would say it's 50-50. We had a lot of the things that they did. We had practiced using the LEM as a lifeboat. Okay, that meant we had to learn how to switch power, get power from the lunar module back to the command module. When we launch, let's talk about it. When we launch, the command module's up here where the people are, and when you get out of space and into the thing, then you turn around and go back and get the lunar module. So now you have two vehicles. I should have brought a model, but anyway, then to keep the lunar module warm and everything, they would connect a power cord over and plug into to make sure that electricity was getting here, running heaters and things like that. So then when you're ready to undock, you undocked and go down. We did that, but now we had to do it reverse. We had to make sure that the lunar module battery power get over because there was no functional electricity on the command module side. So that's one of the ones we did. Beyond that, some of the other stuff we had to do, we had in the simulator, when we'd done all this training with all this stuff, you had assumed the lunar module was a dead animal And we did all the maneuvers with the command module, which has a big engine back here, 1,000-pound thrust engine, called the SPS, Service Propulsion Engine. Suddenly, this is the dead thing, and we're using the small engines on the lunar module to maneuver this thing around. So the thing that was good, Scott, I think, mentioned that they had shut everything down. We didn't shut it down until they were on a track to get back home. We kept the computers running on the lunar module and made a maneuver to get what's called a free return. Let me take that back for a moment. In a free return, when we left the Earth, they were on a trajectory. If you did nothing else, you'd go around the moon and come back to the Earth, which is great if you're landing near the equator on the moon. But if you're a little bit higher, a little bit low, you want to get higher, you have to make your orbit come up out of the plane and then back down. And that means, though, that you would not get back to the Earth. That's what I was talking about before. You'd come back to the Earth, but would you miss it? Okay. So what we did is the very first night, just 12 hours afterward or so, they did a maneuver to return that thing to free return. That is, they just made a maneuver using the lunar module engine, but with the computers to control the attitude and everything. Okay. And then once they did that, then they started powering down everything to shut it down. Now the shutting down was a good thing, everything except crew comfort. I mean, space is outside the cold. You don't have a bunch of heaters to keep the crew warm. They just stayed warm because all the electronics created heat. In fact, you had to pump heat out of the vehicle. It got worse and worse and worse. So in the time when they were on the way home, it was about 35, 36 degrees in there, in the lunar module. And it stayed that way until they got back into the command module and turned on some batteries and so on. But it was still, there was a lot of condensation. They were really worried when they started turning on the command module because it's the circuit breakers and everything are wet, you know, and they have, I think they did a good job in Apollo 13 in the movie, because when they started thrusting, coming in the atmosphere, it's slowing down. It's like raining because all the water was coming out of the control panel onto the crew.
What kind of voltage?
Voltage was 28 volts DC,
No,
and
not a big spark.
not terrible, no big spark, but the things you might kill, things, you know, that are ever attached to it, they quit working on you. And they had AC was, my goodness, I'll call it 100 volts. It's an odd strange. It's not 100 volts and it's not 120. But anyway, so it's up in 100 volts though. You could get a good shock out of it.
So I have a question about the simulators. You mentioned the star balls that had the constellations on them. Was that their only star field that they used?
It's the only star field they use. There was a lot of things. It's very complicated things, and someday next week I always come back and talk about simulators. But we had actually film that showed the planet underneath you. We had movies pre-shot over models so that you could have an 8-inch wide film, and when you look out the window, in each window, you saw appropriately that it was cut off, so you'd only see a circle of the thing, whatever it is. So you'd see the moon go by or the Earth go by underneath you. And it was interesting. You had you'd have 8 orbits around the Earth on one cassette, and then you would switch in a separate cassette automatically, and it would pick up and do the next 8 orbits. Then you go back to the first one, and so on. But it was always on that 8 inches. A camera would move along wherever the hell you should be in latitude. Okay. Then, if you were docked the vehicle, you had, if you were in the command module simulator, you would look out the window and there's a lunar module, okay, but it's flying. And then, or vice versa. In the lunar module, you'd have a picture of the command module. So you'd learn how to fly around and dock and do all the things. Undock, dock again, and so on.
Wow.
So you had a model house. Now, there's no digital anything these days. Okay, this is all electromechanical kind of things. And so inside there was a model house where you'd see a long rail about 20 feet long, and there would be the picture of the lunar module turning around and everything. And there's 2 cameras because the command module had 2 windows looking forward. So they'd come forward and dock. Okay. and they would, and it's two cameras because you're about 5 feet apart. So these two got a different, when you get real close, you'd have a different view of the lunar module top, and vice versa. It was the same with going the other way. Fact is, everybody wanted to come down and see us when we're training. And so Gene Roddenberry and William Shatner came through. They were shooting some stuff in Florida for a couple of their episodes. And they, Pete Conrad happened to drag him in, came in to see the city. Big news is, you know, Shatner's going to build a building and everything. So everybody's just freaking out about it. What they did is, now what they would get in, and they took him up in the simulator and they launched, just like Saturn V. And then they thought they would turn around and see the lunar module and go through this whole thing. But one of my guys, a friend of mine, I was not my guys at that time, I was a grunt, just like he was. But the fact is, he had made the model, the Revell model of the Enterprise. And so they had replaced the lunar module has this a real good model of the Enterprise. And so they turn around and they were freaking out. The three of them up there was because here against the stars in the Earth, here's the Enterprise there, because they don't see any of this. They're playing into a green screen, you know, making them build this stuff and all of these things. And it was so great. And they said, here, and so Pete grabbed his controls, of course, and he went down the left side of the vehicle and around the back and then up the right side of the vehicle, you know. It was just like, whoa, this is so good. And you could just see their minds were working. Okay. And I thought,
That's a great story.
Oh, and that's not even the part of it to get all that. Anyway, it was just then they went on, he's showing more stuff, computers, looking out the window and all that stuff. And all of a sudden I looked at the TV, and under the hot TV lights, the plastic model was melting. The nose is going this way and the tail, the engines are going this way. And I called Gary Probst, Gary, shut down the lights. So he did, shut it down, he saved it, but it was frozen in this new position, okay. But they came out and they were so appreciative of everything that they both signed it. They signed the top of his Enterprise model. And I'm sure somewhere in the world, I hope that thing is still around in his house. Well, that's good, we're done. They go on and do things, you know, and you see that we were all big fans of Star Trek, but there was the 3 seasons and then poof, it's gone. Until, what is it, 71, 72, they came out with the first, it says Star Trek, the movie. That was the name of the very first one. And it was great because here the whole crew is all together and they are on a shuttle-like vehicle. They're being launched up because the Enterprise has been in dry dock, whatever the hell that would mean, up in orbit, but here it is. And so the captain sees his vehicle again for the first time in a long time, and he says, tells the guy on the flying shuttle, he says, let's take it down, take a look. And so sure as heck, with this really good Hollywood model with little lights on and everything else, they flew down the left side of the Enterprise, around behind it, and back up the other side. And I thought, I know how they got that idea. I saw that one.
Yeah, check out Willie's background there, Frank.
Oh yeah, exactly. There you go. It's perfect. It's perfect.
I have a small question to ask.
Sure.
Of the science fiction movies you've seen, which ones were the best?
That's always a good question. I have favorites. Apollo 13, Ron Howard and Tom Hanks did the best job that they could do. I mean, the vehicles, they had 2 simulators, one of the LEM, one of the command module. They put them on our KC-135. So they would go out and they bought 26 flights. Those are each one's a 2-hour flight, and go out over the Gulf and do parabolas. Okay, they go up and down. So they'd get. I want you to just look at the movie again, but think about this: that they would get 20 seconds of zero gravity or something like that. So if you look at it, anytime when there's anything going on that means zero gravity, that it has to be cut off. If they're doing a little thing like with food or water or anything, as soon as gravity comes back and it's back. I mean, so they'd have a thing on the ball, and the airplane is in about 20 seconds, and now come down the other side, and go back to 1G. Well, then all the water that you might be floating here is it's down on you. So they'd go through and they'd clean it all up, make it look right if they have to do it again, and something like that. People got sick. They had all these kind of things. they had the command module and the lunar module had what they call flyaway panels. So in other words, you'd take this panel out and stick the camera in this end and shoot what's going on from the left side to the right side. Then they'd put that one back, go over and take out another one on the other side, and they'd shoot it the other way. So you could see them from the other angle. So every time you see one of these things, the way it's edited together, you just feel that you're right there with them. But it's amazing how many times the 26 men, 52 hours of flying in those airplanes. And in fact, they fly so off, we had to ground them for a while because we had some fatigue in one of the airplane wings, and we had to fix it. And they came back, they waited, get back 3 more months after that and finished what they needed to do.
Amazing.
You know, that's how Ivan Kinslow died.
Yes, that's right. That's right. Well, now that was in a different thing, different airplane, but that's
Yeah.
that's correct.
It's
Yeah,
a big one.
yeah. That was the 170 is
Flying wing.
Yeah, that's it. But
That was
they
about
worked
the
so
last
hard
he
anyway.
mentioned before the plane came apart.
Yeah, he was talking all the way down. Those kind of things. Anyway, that's the one. Now, if you had gone to space yourself, if you were there, then gravity is the best one, because there the pictures of the Earth below you is the best thing. I think the crews have been there. They say that's the best one. Okay. Now me, I like them all for different reasons. Okay. Some of them are worse, like Capricorn 1 and all that sort of things where we're faking it. You know, that was so bad. It's funny, actually. Another story. Gregory Peck came by because he was going to be the flight director on that story, Capricorn 1. And no, marooned. It was marooned. Forgive me. And he wouldn't have been involved with that Capricorn 1. But anyway, and marooned. And so they took him up and did all the same stuff. You know, it's really good. And it was good going. He came back out and he was really impressed. And he wanted to talk to the guys sitting around there, the instructors, about what flight directors do and how you behave. And we could give them our best view, you know, because we pretended to be flight directors when we're playing the roles when you're flying. And it was good. But then there's a break in the action. And I said, this was 67. And he's down there. And one of my favorite movies all the time was The Guns of Navarone. And he was in that. And he had to scale up this cliffs to get to the guns, to the fight. And I said, did you really do that thing? You know, did you really do those stunts? And he said, yes. And it's the last time I'm ever going to do anything like that in my life. He says, it was damn the scariest thing. And so, I mean, just water pouring down on him, all kinds of things. Even if they're not doing a 90, it's kind of like a 45 degree, but it still was a scary thing. And he went on like that, you know. He says, no, that's it. None more of those. I looked at the movie Marooned. I didn't like it either, but that was a whole different thing. He did a good job.
Well, in the room, they also highlighted an interesting point. Our equipment and the Russian equipment don't fit. Of course, that was then. Now it does.
Sometimes
After
our
Apollo
equipment and our
Soyuz.
equipment doesn't fit.
Apollo Soyuz.
Apollo 13.
Yeah, Apollo Soyuz was the first one where we went out and worked together and created an androgynous donkey, that 30 centimeter diameter. So it did work that way. After that, you're correct. Nothing was the same. Nothing was the same. And it still is. I've spent a lot of time in Russia, and I could give you a whole other story about that. I have to tell you one fun thing, though. You're talking about movies at that time, and it's because it's fun to talk about. Barbara Eden came, and with her husband, whose name was Michael Lancero. And he was a big dude. I mean, like not terribly big, like 6'2", and everything. And she's a little thing. But she came in, and this is the height of the 60s. So she was in a white vinyl mini skirt, you know, jacket, all this stuff, and boots. And the problem was when she got in, and it was not Conrad, I don't know what astronaut it was, but anyway, whoever's saying, you had to take off your shoes to get in the simulator. It was just a way to control how much dirt getting in and out. So we had a cutesy little blue box where you sat down and take your shoes off. And then there was a commander, lunar module pilot, command module pilot, put your shoes. Well, he said, she's got to sit down and take the boots off. Now, first of all, there's a crowd behind me on the simulator floor. I mean, because she's just a beautiful woman. So she just needs to sit down and start crossing her legs, and she's unzipping these boots. So, I mean, the place was about to faint. And so she got in, and then the simulator gods said, no, not today. And so she had to come back out with the boots back on. And as soon as she got them back on, somebody said, no, the computer's up. We got to go. So the whole place, it took days to get over that whole episode. Meanwhile, her husband is glaring at this crowd behind me, including me. And nice guy, but he said, God, these guys are just panting, they're good. Any other questions? Otherwise, I'll let you guys time to go to.
Yeah, you were talking about the simulator earlier, and I know the man who designed the optics for the simulators, the Gemini spacecraft and the lunar lander. He designed the optics and for some of the cameras that did some of the terrain following. Al Negler. I don't know if you.
Oh, I know Al. You bet.
You do, okay.
Yeah. In fact, give him my best. I haven't seen Al for a few years now. But that's right. I never put it together when we asked to do this one. But yeah, he's right in that same area up there.
Yes.
Yeah. Well, I'm sure glad to hear that he's still active and carrying on.
Yeah, I just talked to him today, actually.
Well, it's interesting thing, Al, and then there's another guy, and I'm on the spot to come up with his name. But it was not just that they'd show these scenes out the window, okay? But they had a thing they call a panchromatic lens, and it was a flat lens that would make it look like it's infinite distance away. I mean, infinite means 12 feet, 20 feet away. Yeah. And that's what made everything look good. It's the stars. It wasn't like, I know the star ball's only 4 feet over there, but it looks like, because they collimate the light, so it looks like it's coming parallel, And it was awesome.
He had some of the stars on the ball plated with gold, the red stars.
Yes, they've got to get a red one. Now, you need to go up to Binghamton, okay? And do a road trip, you guys, or something like that, because they've got a number of star balls. Some of them are terrible shape because.
Wow, look at this guy's name.
Al Negler.
What?
Look at his name, Bob.
Never mind.
Okay, no problem. But anyway, in Binghamton, at this place called TechWorks, you can go up and see some of these star balls, okay? And we've got the star balls for the Lunar Module telescope are smaller. I think it's only about 9 inches in diameter. So it didn't have 999 stars on it, but it has enough to get it done. And as we're trying to work to put it together, so you actually look through there and get to see the equipment.
Cool.
Think about
Have to make a trip.
Yeah.
Yeah.
It's only what, 2 hours, something like that, 100 miles, 120 miles.
2 hours. Yep.
Yeah.
So I have a quick question if we have time.
Sure.
They could do star sightings from the lunar lander. What did the astronauts see when they looked up when they were out on the moon's surface?
Well, you could see the brighter stars, okay? But you couldn't, if you took a picture, I mean, first of all, we're in daylight. We landed when the sun was about 10 to 15 degrees up. The idea there is it's the best thing when you're coming down because you get the angles and the shadows give you much more relief on the craters. And so we'd get down there. So it's early morning through the whole time. Now, the first guys only stayed outside 2.5 hours. The next day stayed, overnight. Gradually, by the last 3, they were staying 3 nights, so it was a big deal. So the sun is coming up, but still it's only 45, 50 degrees. So the sun is there in your face. And if the sun is anywhere in the field of view, it was really difficult to see anything. If they were in the shadow, like they would get inside the lunar module, so they're blocked out, you could see stars, you could see them that way. But if you take a camera and shoot it, you know what cameras do. I mean, they fix it so they stop it down in that bright area. And
Okay.
we had a telescope that we carried up that was automated, and I can't remember the diameter of it, but it was a pretty good scope. And they ran for weeks and months taking pictures. Okay, there was no problem taking pictures with the right thing. It's columnated, so you wouldn't get any sunlight into it and all that sort of thing. So they were doing pretty good. But I think, not sure they might shoot in UV. It wasn't visible.
Okay.
But yeah, that's one of the big things about, you can't, there's no stars, but they were there, but it was the same thing. We could see on the back of the moon, or the back of the Earth, you could see stars. Now it's better on the moon because there's no atmosphere. The atmosphere on Earth never stops, it just gets less. So even at 200 miles, a lot of molecules out there. So in the day shift, it's hard, the day side, hard to see the stars.
Mhm.
During the time, the cameras we take now, when they do nice, you can see, just go to nasa.gov or any of those things and look for videos of what they see up there. Videos are all different than still pictures. You know what I mean? You get a lot different, but you can see incredible things that are going on the surface below you. That is in terms of like aurora, stuff like that, and thunderstorms. Some of them, if you look at the thunderstorms that they've got on there, and the fact is, I don't know if you know what sprites are, but they would figure out that lightning is going on, it's hammered to the ground, but there's just as much lightning going up into the ionosphere because it's like a big electrodynamic generator. And so all this electricity is flowing all the time. Just find some time and look at the movies from the space station anytime.
It's interesting. You touched on something. I was with some friends, and a couple of people there were teachers, and this one woman, she was teaching students at like middle school. She took a poll. Three quarters of them did not believe that we went to the moon because we didn't have the technology. That's today's students. I was blown away by that.
That's
but
crazy.
The problem is that it's an unintended consequence of the internet. The fact is that if it's on the internet, they believe it. So,
exactly.
And so it used to joke about this, and in Hyde Park in London, if you had a kook, that person could go in there any time of the day or night and stand on a box and say whatever they wanted. Okay, but the only people who get impacted was the people gathered around him. 20 people, 10 people, 5, 1. Okay, now any kook can get on to the internet and blast this out and hit millions.
Have you seen this book,
True.
Frank?
No.
Oh
Yeah, that's a good book.
Phil, Phil is great. You bet.
No, in Hyde Park in London, there's a sculptor made a soapbox. It sits on the ground, and everybody stands on that sculpture
Just to take
give
a picture.
their opinion of
Yeah.
all the profanity the Parliament is involved with.
That's it. But you could see that limited. So somebody's kooky ideas only got that far. Now
Oh yeah.
they're everywhere, and people. It's okay. They just have to come along the way. Maybe that's just what happens. I've always thought if there are aliens, and I pretty much believe that there are, they go by and check on us periodically, and they said, "No, not yet."
You've heard the joke.
My thing is, if there are aliens and they want to come down here, they definitely wouldn't show up in person. They'd throw a few rocks at us first, soften up the target, and then annihilate who's left.
I think that's it. Could you treat it like they should quarantine us, until we get better? Yes, probably. Or I think it the other way. It's like 2-year-olds in a sandbox because we're just arguing over possessions, toys and things like that. And there's a level at some year in the future where we get past that. Either we blow ourselves up or we get more mature.
Blow ourselves up because somebody thinks they're bigger than the other guy. And of course, it's a politician because they do not believe in consequences of their actions.
That's right. That's right. They
For all.
love to
Didn't they
say.
get us into the last, was it 6 wars?
Yeah.
Or they think they're smaller than the other person. That's the bigger problem, I think.
Great. Have to act bigger. Well, thank you, Mr. Hughes.
It's my pleasure, guys. It was fun.
And good night.
Absolutely.
Thank
Very
you
nice.
very much.
Guys,
That
take
was
care.
such an interesting presentation.
All right. If you ever
Very,
have
very
questions,
interesting.
every time you have questions, get in touch with me, okay? We can take care
We
of it.
will, we will. And if you want to come back and talk about simulators, that would be fun too.
Sure. Back next year. In fact,
Okay.
if you were ever going to Binghamton, I would tell you
Shut this
more
off.
about it, and then you could go up and get more out of that trip, something like that.
Oh, okay.
And you're in Florida.
I
What the heck are you doing? You're not even looking cold.
Well, it's been Florida, for Florida, it's been cool for the last few days. It was 44 this morning.
Oh, my God.
It's cold.
That's
Yeah,
true.
they're getting a frost north of us tonight.
Oh, yeah. And I'm in Houston. It was 42 this morning, and it's going to be 29 Friday night, so
Oh,
the life
man.
goes on. Our new environment, our new attitude. Take care, all. See you.
Okay, thank you again.
Thank you so much.
Thank you.
Bye.
Bye-bye.